Reduction of R&D costs is everywhere in pharma nowadays. Have you ever been asked to decrease the number of repeats within experiments or in between experiments? After all, dose response curve fitting is easier and we can test more candidates. Sounds like a great idea, but is it truly? Today, let's talk about the minimal number of repeats to trust EC50s, or when cost saving starts to become a bad idea. Let's take an example. Let's consider A549 human ACE2 human TMPRSS2 cells infected with SARS-CoV-2 in presence of compound, and 1 day later, the viral nucleoprotein stained for high content imaging and determination of the percentage of infected cells. The actual analysis method for that assay was described in one of my previous videos, which I link here. The question today is how many independent repeats should I perform to trust EC50s from such an assay? And linked to that, how many independent repeats should I perform to be able to trustfully compare EC50s between compounds? The first step is to check that the EC50 of reference compounds actually follows a normal distribution. Start as soon as possible during assay optimization, and if need be, re-optimize. And then, just around the assay qualification or validation, please check the usual 2 independent runs that are performed before the assay qualification or validation, then the 5 independent runs during the assay qualification or validation, and please add another 3 independent runs after the assay qualification or validation, so that you arrive to a total of at least 10 independent repeats. For each reference compound, check that the 10 independently determined EC50s confirm normality. You can do this, for instance, with GraphPad Prism, using the analyze, then normality tests, then D'Agostino-Pearson and/or Shapiro-Wilk tests. If a normal distribution was observed during assay optimization, likely it will be confirmed during assay validation or qualification. If that is, however, not the case, you can try to log transform the data. In most cases, less than 30 independent repeats will have been performed. In that case, the mean EC50 should follow a probability density plot for a student's t-distribution. Such a plot is shown on the left. The lowest curve, the most bottom curve, corresponds to a degree of freedom of 1, then a bit higher of 2, and you will appreciate that from a degree of freedom of 30, the line in red is almost identical to the normal distribution. On the right, you can find the critical values, or z-score, for 2-tailed tests following the student's t-distribution. The column highlighted in green corresponds to an alpha value or significance level of 0.05. In other words, corresponding to a confidence interval of 95%. In that case, the CI95 for the EC50 can be determined as follows. It is the mean plus or minus the ratio of the z-score for 2.5% and a 2-tailed test, multiplied by s, so the standard deviation, and divided by the square root of n, the number of independent repeats. This ratio is actually called the measure of error, or MOE. This is important because what we truly want is to determine the CI95 properly. To evaluate and calculate the minimum number of independent repeats that should be performed, the MOE equation can be used and converted to the following. So n equals to the square of the ratio z-score for a 2.5% and 2-tailed test multiplied by the standard deviation and divided by the MOE. During hit-to-lead or lead optimization, a rather loose MOE can be used, And usually one wishes that the MOE equals to the standard deviation. In that case, the equation for n becomes as follows. So n should be higher than 2.4 to the square, and that means around 6. So practically, at least 6 independent repeats should be performed to trust the EC50. If now you have a drug candidate, a more stringent MOE should be used. I personally find it a good idea that it depends on the value of the mean. So one may wish that the MOE equals to 1/10 of the mean. And then n becomes, so the number of independent repeats becomes the square of the ratio 2.4 multiplied by the standard deviation multiplied by 10 divided by the mean. With that, it is likely that you will have more than 30 independent repeats. Then, the probability density plot for a normal distribution can be used. Such a plot is shown on the left. You will appreciate that a little more than 95% of the values are located between mean minus 2 standard deviation and mean plus 2 standard deviation. Actually, the z-score is not exactly 2, but 1.9596 as shown on the right. And so you can use the same equation as before, but replacing 2.4 with 1.96. In conclusion, it is definitely not a good idea to decrease the number of independent measurements to 3, as is often recommended, or to 1, as I've heard a few times. Ideally, during hit to lead or lead optimization, you want 6 independent repeats. If that is practically not possible, an offset strategy can be to really make use of 384 or 1536 well plates. In that case, you could plan 2 to 3 independent repeats, each with 4 technical repeats. For your final drug candidate, please estimate the appropriate n, so number of independent repeats, depending on the mean and the standard deviation of the assay. The only exception is for HTS or high throughput screening, where of course 6 independent repeats are not possible. However, please plan at least 2 independent repeats every time you can. Finally, only consider valid measurements, repeat if that is not the case, and report n in your scientific publications. And you, do you have any advice on the minimal number of independent repeats? Or any advice on how to save on R&D costs? If that's the case, looking forward to your comments below. Thank you, bye bye.